Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we have Roman Luchin here he actually works at Microsoft Research at Station Q in Santa Barbara, and he's visiting today. He graduated from University of Minnesota and then spent 3 years at University of Maryland before coming to Station Q, where he has been for a year, just about a year. So he is going to talk to us about topological quantum computing with Majorana Fermions. Roman?
Thank you very much for introduction and for the invitation to come here and give a talk. It's always a pleasure to visit Redmond. So this is Microsoft Station Q. This is a view from our building. We are located in very nice campus, UCSB campus, and our group consists of mathematicians, physicists, and computer scientists. And what we are trying to do, we are trying to explore this interface between three different disciplines to build a quantum computer. And the particular approach that we pursue is topological quantum computing. And I'll explain today what this is about and why this approach is very promising. So most of the people in our group are theoreticians, but we also coordinate with many experimentalists around the world, and we just ask them to do some experiments to test our ideas. So this is the outline for my talk. I'll start with some introduction of quantum computing, and I'll explain why it is advantageous, and then I'll explain what is topological quantum computing and present some realistic systems where we think we can implement this approach. So as you know from everyday world, that most of the physics, most of our everyday life can be explained in terms of classical laws. Newton's law, Maxwell equations of electromagnetism, etc. But if you scratch the surface, we can quickly realize that the world is actually quantum mechanical. And these are devices that we use in everyday life. And some of the things in those devices is actually based on quantum physics. In transistors, tunneling is a particular quantum phenomenon. In lasers, the fact that you have a discrete two-level system, so you have quantization of levels, is also a quantum mechanical phenomenon. In MRI, the fact that atoms have nuclear spins, nuclear spin is also a quantum mechanical object. So I would say we use these properties in everyday life, but we use them not to the fullest extent. And in order to do that, we have to go back to the principle. In order to explore quantum mechanics in depth, we have to go back and use the most fundamental principle of quantum mechanics, the principle of superposition. So if quantum mechanics postulates that if you have a state, psi, then this state can be a superposition of two other states, 0 and 1. And principle of superposition can be illustrated in this very nice experiment, double slit experiment, which we all know and love. So if the light the light is a wave. So principle of superposition is just the fact that we add the amplitudes for the light, and because we add amplitudes, not probabilities, we can have this interference pattern on the screen. So the idea is you send the light here and here, and then the light can go either through this path or this path, and then depending on the position on the screen, you'll see a sequence of these dark and bright spots. And so that's this principle of superposition, because you have to add the amplitudes for electromagnetic field and then squares the amplitudes to get the intensity on the screen. So a long time ago, in 1982, Richard Feynman, very famous American physicist, asked the following question. Can we explore the God-given resource, the resource of quantum mechanics, for something useful, for quantum computation, for example? So if you do that, then you immediately realize that because each state of the system, if it's a two-level system, can be in superposition, then if you have n such two-level systems, then the information that is encoded in these two in such a system scales as 2 to the n. So it scales exponentially with the size of the system. And that's actually something we are trying to explore in quantum computing. We're trying to explore the fact that we can store much more information in quantum realm than in classical realm, where you can just have 0 and 1s. So what is the potential application of quantum information processing? Actually, there are many. And for example, if you want to solve a system, and we would like to understand, say, properties of a particular system, like a chemical reaction that involves some quantum mechanics, then we can simulate that on this quantum computer. So we can basically solve any quantum system by just programming it into our quantum computer and running the simulation. Another application is factorization of large integer numbers. And that basically triggered this interest in quantum computing because this particular operation this particular algorithm leads to exponential speedup. So our security will be in danger if we have a quantum computer. Or maybe we can invent something more complicated, quantum encryption. Another thing which is fairly useful is quantum search algorithm. And it's basically a search of an entry in a database, but here we have algebraic speedup rather than exponential. But it's also very useful. And finally, quantum cryptography. So quantum physics allows you to send information securely, and the security is guaranteed by the physics. And so these are just a few potential applications. People are working and discovering more and more algorithms. But what I would like to talk today is actually how to build a quantum computer. What are the systems that are suitable to do this task? And Krista here, she is doing research on quantum algorithms. So if you are interested, you might want to talk to her and learn some more details about this. So in classical computer, we have a bit, which is a basic logical element. It has 0 and 1. So we need to find something similar in quantum computer. And it's called qubit or quantum bit. Essentially, qubit is a quantum two-level system. So these are the two levels. And by controlling the coupling, so very often two-level system is represented by spin. So you can have essentially Pauli algebra. And if you control all the couplings, with a spin, then essentially you can program the state you want to get. So a qubit is a controllable two-level system. You can drag this vector by applying some gate voltages and signals and changing these coefficients. You can drag this vector and put anywhere on a block sphere you want. So basically you can change all the coefficients here and here. And so that's an idea. So you would like to have a controllable two-level system. Well, these are the potential realizations of these controllable quantum two-level systems. And I would say they come in two flavors. So the first one is based on microscopic degrees of freedom. So like a nuclear spin in MRI, this is a microscopic degree of freedom. Or position of an atom in particular location, that's also a microscopic degree of freedom. And another type of qubits is based on collective degrees of freedom. And these are superconducting qubits and actually also topological qubits that I will talk about today. So the idea is that a lot of electrons, they behave in a coherent way, so that it's like an orchestra. You listen to orchestra and you see that everybody is following the same pattern. So the same thing happens here to the extent that you can describe 10 to the 9 electrons by a single variable. So that's what happens in superconductors, and in topological qubits we would like to have that, but even go beyond that paradigm. So what are the problems in quantum computing? I mean, these approaches are fairly developed now, and people have created these two-level systems. They manipulate them, they couple them, and try to play with them. But there is a fundamental problem, and the fundamental problem is called decoherence. So if you have a microscopic system and you want to couple to this microscopic system and control its position on a Bloch sphere, it turns out that there are other couplings which are unavoidable. And we cannot just filter out useful couplings and say from unuseful couplings. So these unavoidable, say, harmful couplings lead to errors in our quantum computation. And this process is called decoherence. So that's why we talk to experimentalists, because quantum phenomena occur in the lab, and in the lab you really have to make your hands dirty, and so the process of quantum decoherence, something that people know from the lab experiments, and they measure it. So they start in some state, and then they see that this state will decay to a ground state, for example, if you start in the excited state with time. So your information can be preserved for some time. And we would like to actually try to correct these errors, but it turns out that unlike in classical computers where error correction is very developed and fairly successful, in quantum computers it is very hard to do. And the reason it is very hard to do is because if you want to correct more and more, you need to introduce more and more resources. So there are some approaches where people established what should be the error rate, and this error rate is 10 to the minus 5. So it's fairly small, and so far we are trying to achieve this error rate, but it's very hard. So yeah, so you have a decay time and you have a speed of particular operation. So if you divide these two, that will be your error rate. Excuse me?
How well can people do today?
It depends on particular system. So I think we are reaching 10 to the minus 4 in certain qubits. But the thing is, there is something unexplored here. This is error rate for some models. And if we scale the system, this actually decay rate might also scale with the size of the system. So this area needs to be explored more, especially when you have more and more qubits together, because there is also a collective effect. But what we are trying to do at Station Q in Santa Barbara, we are trying to solve this problem in a different way. We're trying to find a system which will be immune to these errors at the hardware level. So rather than having to correct for these errors, we would like to build a hardware which is fault-tolerant. And the idea for this approach actually goes back to somebody who spent a lot of time here in Redmond, Alexei Kitaev, who is now professor at Caltech. And he said the following thing. He said, well, let's try to encode our information in very non-local degrees of freedom. And the errors that we usually have, they come from some local fluctuations, local changes in the environment. But if you have, if information is stored non-locally, then it will be insensitive to this local perturbation. So you can think about this in using a topologist view. And topologists, they say, well, these three objects are actually identical. They all have just a single hole. So as long as we don't do anything drastic to the system, as long as we don't destroy this whole, the information which is encoded in this geometry will be protected. You can bite a piece of this donut and the information is still going to be preserved. And so that's the idea. You would like to find a system which will be insensitive to these local perturbations because we encode the information in a completely different way. So usually we are talking about topological phases of matter. These are phases of matter where experimentally observable quantities can be insensitive to local perturbations. And one of the well-known examples in condensed matter physics is quantum Hall state. Quantum Hall state is a state of a semiconductor in a strong magnetic field. So these two discoveries actually were awarded Nobel Prizes in 95 and 98, and there is some difference between them, but I don't want to go into details. As far as this is concerned, this is the topological phase of matter. So if you take an integer quantum Hall state, which is a state, say, in lower magnetic field, and you apply electric field to the system, then there will be a current flowing in the perpendicular direction. And then if we just measure this current and find a whole conductivity of the system, this is essentially the coefficient proportional to the electric field applied, what you'll find that this coefficient will be proportional to fundamental constants, e squared over h, times the integer. And this integer is accurate to 10 to the minus 9. So you take a sample with different geometry. The sample can have different disorder realization, different parameters, but still this quantity is protected to 10 to the minus 9. In fact, this whole conductivity is a standard of resistance now.
And again, you're talking about the lifetime of this integer, not about... I mean, the integer is accurate to 1, not to 10 minus 9.
No, you measure something, and something is close to 1, but how close is it to 1? Right? So I change parameters in the system, and it still stays in 1, whereas in some other system, non-topological, you change something, this coefficient will change completely. It's going to be 0, or it's going to be 10. So what the point is that this integer, this number, is close to 1 with the accuracy 10 to the minus 9. And it doesn't matter what I do to the system. I
guess
change.
another way to say it is if n was a billion, it wouldn't be a billion and 1 or
I see.
999.
It is always an integer.
Yeah, I get it.
It's an integer, but it's accurate integer too.
Yeah. Yes.
So I'll ask you a question as an ignorant about this field. So there are the software approaches to error correction in quantum computing, and what you propose is kind of hardware approach toward that kind of uses replications, right? In a sense, is what happened, that the state is not captured by a single particle, instead it is captured by a lot of repetitions. So what is the fundamental difference here? Why not do it in software and just have so many repetitions?
Well, I mean, if you refer to collective nature of the degrees of freedom in which we are encoding information as repetition, then in this sense, yeah, there is some similarity, but you have to realize that there is just a single parameter that characterizes a system which consists of 10 to the 10 electrons, and we don't have to control each of the electrons. It just happens that the nature does it in a particular way. Now, if I have a large system, then the number of electrons can be 10 to the 23 or even larger, and I don't have to control each of them. But I can characterize the state just by a single parameter. So it's different from error correction, where you control different elements separately, right? So there are similarities and there are differences. Okay. Did I answer your question?
Probably I need to study more physics to understand.
Okay. So So that's an example of a topological phase of matter. That's the phase of matter which is the state of which is not very sensitive to local perturbations. And what we want to try to find is a state which is similar but has additional properties. It's even more sophisticated state of matter, and it's called Non-Abelian topology. This phase is called Non-Abelian topological phase. So once you find such phase, and I'll give some examples where we predict these phases can occur, we also have to be able to manipulate certain excitations in these systems. They are called quasi-particles or anyons. So these are the candidate systems, and in today's talk I will spend some time on superconductors, and I'll show you that superconductors are very interesting systems which can actually be engineered. So in some sense, we are trying to engineer the state by combining various properties of different materials. So I mentioned the word non-abelian, and this word non-abelian is at the heart of the topological quantum computing proposal. So let me explain why this is so. When as a freshman, in the graduate school, I took quantum mechanics. I was taught that there are bosons and fermions. There are two particles, bosons and fermions. But that's true only in three-dimensional world. And the reason it's true in 3 dimensions comes from this argument. So we know that if you take a wave function of the system and try to exchange two particles, then depending whether they have bosonic or fermionic statistics, the wave function will pick up a plus or minus sign. And the reason there are just these two possibilities comes to the essentially a triviality of a braid group in 3 dimensions. So if I exchange these two particles, and then I will exchange these two particles twice, so essentially I return to the same point. So I did some operation on the system, but I can deform this loop. I can essentially take advantage of this degree of freedom outside of the board and essentially deform it to a zero, to a point, which means I have to return to essentially the same thing, and which means that this operation of exchanging t squared should be equal to 1. And if t squared is equal to 1, the only possibility is that t is equal to plus minus 1. And that's why you have only bosons and fermions. But if we take 2 dimensions, in 2 dimensions we have more possibilities because we don't have this degree of freedom. We don't have, if you constrain our particles to the plane, we don't have this degree of freedom. And so these exchanges are actually non-trivial. So you cannot deform it to, this argument doesn't hold. And that was the prediction made by 2 Norwegian scientists, Leinas and Myrheim, and also Frank Wilczek from MIT in 1980s. And it has been realized later that such particles exist in these 2-dimensional systems, quantum Hall systems, and there are situations there where when you exchange, you pick up the phase, which can be anything. That's why these particles in 2 dimensions are called anyon, which means any phase.
Shouldn't it be non-abelian statistics?
Should be non-abelian statistics. Non-abelian statistics happens when you have degeneracy in the many-body ground state. So let's imagine we have many states which have the same energy, and then such exchanges that I'm talking about here can induce certain transformations between these many-body ground states. So then I cannot just describe this operation as just a phase. It can be described by a matrix. And that's something that we are trying to exploit here. We're trying to exploit the fact that when you have non-abelian statistics, then exchanging different particles between each other can be explained in terms of different matrices. And matrices do not commute, so we can make various combinations and encode information in these states.
So small b there is a summation index.
Yes.
Just see what the x's are on that. X1 exchange with x3.
Those are
Yeah,
particles.
so we have a...
So you have to have
Yeah, you have a state which has many particles, xn, so x1, x2, and I'm writing a wave function which explains the state. And then I can take two particles from this state and try to exchange them together. So I can exchange x1 and x3, and that will be described by a matrix M. Or I can exchange x2 and x3, and that's going to be explained by a matrix N.
And the intuition is why this doesn't happen in 3 dimensions?
Because in 3 dimensions, as I explained, the exchange is very trivial. The braid group is trivial. So two exchanges give you just one. And so the square root of 1 can be either plus or minus 1.
So there is an implicit point singularity behind all this. You were referring to additional degree of freedom where you can pull the loop to a point. But if you puncture the plane, you cannot pull the loop to the point.
Yes.
So what is the singularity what do you puncture in both cases?
Well, you have a particle, physical particle, sitting somewhere.
Right.
And if you can go around this particle,
I see.
then you can avoid the singularity. But if you don't have a degree of freedom, it's like having a plane with defect which has a line, and you cannot just go around the line. So that's the difference. That's the way to think about it. And the reason we are trying to avoid, we can avoid decoherence here, because these manipulations never involve excited state of the system. So in the previous proposal, where we had quantum bits, but say conventional quantum bits, they always involved excited and ground states, so and some superposition between 0 and 1. And we know that, well, excited states, they decay, so they relax to a ground state, so for lifetime is limited.
So that's what we've been saying, but I just don't understand it. I mean, I can have a spin half guy, half up, half down. And there's no excited states, it's just a linear combination of two states gives me another state, there's no energy involved. It doesn't have to be an excited state.
Well, that's not an eigenstate of the system. This superposition is not an eigenstate of the system.
Depends on the system. I can have, right, I mean, superposition doesn't have to be an excited state and a non-excited state.
Well, 0 and 1 refers to ground state and excited state, right? And you're saying it's a superposition?
Why does it have to?
Not just spin.
Well,
I mean, if it's spin and there's no magnetic field, then I can have a linear combination. I'm just confused as to why you're saying that you have to have an excited state in a superposition.
right. So, okay, maybe I'll just draw something here. So this is a two-level system. This two-level system has a ground state and an excited state.
I think you better go on. What's wrong there? I mean, I can write 0, 1 side by side, 2.
Then it's a degenerate two-level system.
Yeah, right.
So
Then I have a superposition.
So if you have a degenerate two-level system, then it's kind of similar to what I'm saying, but this degeneracy is many-body degeneracy. So the reason it doesn't work if you have a degenerate two-level system, which is kind of local, because you add some small perturbation, and this degeneracy is going to be splitted. So this degeneracy is accidental, and you change something in your apparatus, and this degeneracy is gone.
For example, a very small magnetic field from somewhere.
Exactly.
Let spin up and spin down for you.
So this is not a robust degeneracy, but you're actually getting to the point that I will explain in the next slide. So you would like to create a degenerate system which is robust to these small perturbations. And you're trying to use these degeneracies, robust degeneracies, to encode the information. Okay, so that's the basic idea. That's why if you have a state which is non-Abelian state, then you do manipulations in the ground state, doesn't invoke any excited states, and the information is going to be robust. And this robustness will be guaranteed by the quantum mechanics, by physics. So it turns out that the particles that the state that satisfies these properties is the state which carries Majorana fermions. So that's why my topic today was quantum computing with Majorana fermions. If you find Majorana fermions, then you'll find a state which will satisfy these properties. So what is Majorana fermion anyway? We know about fermions. Now what is Majorana fermion? What's so special about this Majorana fermion? It's an interesting object which was predicted long time ago in 1937 by Ettore Majorana, who asked the question in the context of high energy physics whether whether the Dirac equation, which describes essentially spin 1/2, which corresponds to spin 1/2 particles, has to be necessarily complex. And then he showed that by choosing a particular representation, you can make equation real, and therefore there should be a real solution of this equation. And if there is a real solution of equation, then essentially the particle will be the same as its own antiparticle. And since then, there has been a lot of search in particle physics, high energy physics, supersymmetry, which is also related to high energy physics, and also solid state systems. But as of now, we don't have a convincing evidence for their existence, and I would like to present one road to overcome this problem, and I'll present concrete proposal where we can find these Majoranas.
I have a quick question before I gave it. So take your Dirac's equation and split it into real imaginary parts and write down twice as many equations. They're all real. So there must be something more going on there. That's the first question. The second question is, why are they called fermions if they're really anyons?
Well, they obey anti-commutation relations, which are fermionic. And now, if you really split Dirac equation into two, I mean, you can always split complex number into real parts.
Right, so what's
But the point is that in this Majorana presentation, there is no complex part. There is just real part. So if you count degrees of freedom, it's a real equation. A real equation has a real solution. So if you have a real solution, then it means that the complex part is gone. But I'll also get to this in the next slide. Actually, in this slide.
Some real equations have complex solutions, right?
Yes,
So what
No, you can always, they can have complex solutions, but if you have a real equation, you can always find a basis where there is a real solution. If you have a complex equation, there is no basis where you find a real solution. So really, this Majorana fermion is a real, you can think about it as a real part of Dirac fermion. And if I want to construct a Dirac fermion, I have to take these two Majoranas. So our intuition actually comes from having Dirac fermions. You know, in metals, we describe everything by Dirac fermions. And this Dirac fermion that I create from two Majoranas is very special because it's now a composite object, and these two Majoranas, as depicted in this picture, can be far away from each other. So essentially, we created. If you have Majoranas, you'll have a fermion which will be, very non-local, and this non-locality helps us to make protected systems against decoherence. Yes.
I have very basic question because I'm not a physicist. So the state here is represented by the relative position of the two particles. Is that?
The state is represented here by the fact whether it's occupied or unoccupied by particular Dirac fermion. So I created artificially this Dirac fermion, okay, and now I want to enumerate my Hilbert space, my states. And I can enumerate by either saying, well, this mode is unoccupied, then it's 0, or it's occupied, which is denoted by this, then it's kind of 1. And so my logical qubit is a qubit which is either occupied or unoccupied by this Dirac fermion. And because of that, if I have many of these particles, then from 2n Majoranas, I can roughly create n qubits. And so that's the idea. You have these Majoranas on the plane, and you have a Hilbert space that they correspond to, and this Hilbert space will be degenerate because these Majoranas, they are sitting at 0 energy. So there is a degeneracy involved.
So can you explain in which sense this is a Dirac fermion?
Well, it's a complex, right, object. So each of these two are real, but now if I conjugate this, I'll pick up a minus sign. So the definition of Dirac fermion is that C and C conjugated are not equal to each other. and Majorana fermion, they're equal to each other. So it's essentially a half of degree of freedom. So one Majorana is a half of Dirac fermion. It's only a real part of Dirac fermion. So, so now I wanted to illustrate why exchanging these particles will actually lead to something non-trivial, and why this happens in this system. So suppose now I make the situation a little bit more complicated. I add another Dirac fermion, which is localized between A3 and A4. And then I can say, well, my Hilbert state, my Hilbert space can be encoded in either this mode, occupied or unoccupied, or this mode, occupied and unoccupied. And there are 4 states which essentially enumerate this Hilbert space. And now I can do something very non-trivial, because I can take a half of my fermion, which is encoded here, and exchange with another half of the fermion, which is encoded here. So normally, in other system, you would take one electron and exchange with another electron. But here, because this electron is very non-local, it's actually a composite object, you can take a half of electron and exchange with another half of electron. And that's why we are doing something non-trivial. And if you just check the math, you will find that the state you will end up will be different. And that's basically a simple quantum gate operation. Red and blue.
Are all the Majorana fermions there distinguishable, or are they?
Oh, there is no significance. It's just it's just labeling which ones we are braiding.
So that gave you a Hadamard gate, basically.
Yeah. So this is the excitement in the community because of these ideas, and the reason there is so much excitement because we found how to borrow a trick from a superconductor and use this trick to find the systems where Majorana fermions can be detected. And the idea is the following. So I'm going to give us some sort of introduction for superconductors. But if you guys are familiar with superconductors, I can just skip it. So should I? Okay. So superconductors are actually very interesting superconductivity is a very interesting state of matter. It's a state of matter where at low temperatures, once you lower the temperature, the state doesn't have any resistance. So if I take a mercury and I lower the temperature and measure the resistance of mercury as a function of temperature, then at some point the resistance is essentially vanishing. And that was discovered by Kamerlingh Onnes in 1911, and soon after discovery, 2 years after discovery, he was awarded the Nobel Prize. And the theory of superconductivity remained unsolved until 1957, where these 3 theorists, Bardeen, Cooper, and Schiffer, came up with the explanation why this happens, why you have zero resistance state at low temperature. And the basic idea is that electrons in a metal, they kind of glue to each other and they form Cooper pairs. From 2 electrons, you can create a boson, quote, which is called Cooper pair. And bosons and fermions have very different properties. At low temperatures, bosons want to occupy a zero momentum state. They want to condense and sit in the same level, whereas fermions, they don't want to do that. And so, and that actually is an explanation for this zero resistance. Bosons can have zero resistance because there is coherence between them. But there is another property which is important in the theory of BCS. The theory of BCS has the state, the Hamiltonian, the effective Hamiltonian that is described by the in BCS theory mixes states with different particle number. So the particle number is not conserved. And that's actually key to having Majoranas, because if the particle number is not conserved in Hamiltonian, and I wanted to say that the theory of superconductivity is so developed that we can even explain this cool stuff. When we have a magnet on top of superconductors, this magnet can be levitated because of the Meissner effect. So we know superconductivity pretty well now, at least conventional S-wave superconductivity. But I was going to say that this fact that superconducting Hamiltonian doesn't conserve the particle number is actually key to the following observation. So in order to diagonalize the Hamiltonian, which doesn't conserve particle number, I have to have a superposition between sort of particles and holes, or particle electron creation and annihilation operators. And this superposition has some amplitudes u and v. And if I want to create the Majorana fermion, all I need to do in a superconductor is to find a state where these two amplitudes are actually the same, well, up to conjugation. Then you can just check, because psi goes to psi daggers, that if u is equal to v star, then you'll get a particle which will be self-conjugate. So that is a Majorana fermion. So where do we find these states at zero energy? Well, where do we find these states with such properties? Well, we find them whenever we have an equal superposition of a particle and a hole. And where do we find such superposition? Essentially, somewhere between somewhere between the empty and occupied band. So somewhere here. So we have to look at zero energies. And if you find a state at zero energy, such state actually by construction will have these properties. And the reason that it has by construction these properties actually is something fundamental in the theory of superconductivity. There is certain symmetry in the theory of superconductivity, which is called particle-hole symmetry. And this symmetry tells you that if you have a solution which corresponds to energy E, then there should be another solution which corresponds to energy of minus E. Now, if I have a solution with zero energy, you can just check that this symmetry guarantees that U should be equal to V star. And therefore, the state that is sitting at zero energy will be self-conjugate. Yes?
You mentioned spinless fermions. I thought the rule is fermions have to have a spin 1/2.
Yes, that's right. This is a model for now, but I'll give you a physical realization later. I'll show you how one can enslave the spin. So, so basically, we are guaranteed to have the zero energy state if, as you correctly pointed out, we have spinless fermions. Now, the zero energy state is not going to be accidental like in the other example. It's going to be protected by this symmetry. Because see, this symmetry tells us that we should have states that come in pairs, E and minus E. Now, if I add some perturbation to the Hamiltonian and I try to lift the state from zero, then it's not going to have a partner. And since it's not going to have a partner, that should violate particle-hole symmetry. So these changes are not allowed. So unless we do something drastic to the system and we completely destroy it, weak perturbations do not lift the degeneracy. So it is robust. Okay. Now, I'll give you some examples of spinless for now, but then I'll show how one can engineer the spinless Hamiltonians from spinful fermions. So why do we have these zero energy states and where do we have these zero energy states? So there is a simple model which one can write, and it's a superconductivity model where the order parameter is proportional to momentum. So this coefficient depends on momentum. It's proportional to P. And within this simple model, what I wanted to illustrate here is that without any fine-tuning, you will have these zero energy states. So let's imagine that we have a situation where this chemical potential is sort of varying in space, like this. Then whenever chemical potential is positive, we have a metal. Whenever it becomes negative, we have an insulator, because there is no Fermi surface, so there is no the fermions cannot populate. There is no the density of states is zero. So if you assume this configuration, actually this configuration models the one-dimensional system with ends at these points. Now I'll do another simplification, and I'll say that, well, this chemical potential changes very slowly in space. Okay? Then I can drop essentially higher order derivatives, and what I end up with is something well known in high energy physics. It's called 1 + 1 Dirac equation, which we are solving for zero energy. 1 + 1 Dirac equation is very well studied, and in particular it is well known that whenever the mass of this Dirac equation, which here plays the role of chemical potential, changes a sign, you'll have these states. You have some bound states. In other words, you don't need to know high energy physics. You can just say, I have this equation, I want to find a normalizable solution of this differential equation, and what you find that there are normalizable solutions at the ends. So bottom line, if I have this spinless p-wave superconductor, at the ends of one-dimensional system, I'll have zero energy solution, and these zero energy states will be robust against small perturbations. So I don't need to fine-tune any parameters like delta or mu or anything. As long as I have a p-wave, spinless p-wave superconductor, I'll have these states. So that's the idea. We need to somehow engineer a spinless superconductor. How can we do that when all electrons have spin? So there are two ingredients that we will use. And first ingredient is spin-orbit interaction. So spin-orbit interaction is an interaction which couples spin to momentum. And if you can somehow enslave spin to the momentum, we can get rid of this half of the degree of freedom that is redundant. And we can make the system effectively spinless. And the second thing is superconducting proximity effect. So we want to induce, rather than looking for these materials in nature, we want to have the superconducting state on demand. So then we'll use some other superconductor and create some interfaces, and at those interfaces we will have the necessary states. So I'll be talking today about superconductor, semiconductor heterostructures. And these heterostructures will have essentially the required properties. So first, let me just spend a few minutes on spin-orbit coupling. Actually, spin-orbit coupling in condensed matter systems appears quite generically. It appears because at the interface between different materials, you might have an electric field. It's a very strong electric field, in fact. And then if the motion of electrons is, say, constrained to this plane, then if I make essentially a Lorentz transformation and go to a rest frame of this electron, this electric field will induce a magnetic field in this rest frame, which will be pointing up. And if the electron has a spin, obviously it interacts with magnetic field, so therefore I have a coupling between the spin and an electric field. And this is this effect is called, this mechanism is called Rajba mechanism, and this mechanism can be written in terms of in this form. So I will use this in the rest of my talk. And what is important for this Rajba spin-orbit coupling, that it actually does the job, because now you can see that the spins are enslaved to the momenta which live on different Fermi surfaces. So the spins, they precess around the Fermi surfaces either in clockwise or counterclockwise fashion. The second ingredient that I will need is the proximity effect. So what is proximity effect? Well, you have a semiconductor and you put it very close to superconductor. So electrons in the semiconductor will tunnel into superconductor. And for some short time, they will feel these correlations, superconducting correlations. So they will inherit these properties from the superconductor. And effectively, it's a way to create a Hamiltonian which doesn't conserve particle number. Because what I can do, I can send in an electron and then measure and this electron will be reflected as a whole, and as a result of this, the Cooper pair, the 2 electron, will be emitted in this superconductor. So if I want to describe this kind of special scattering that appears at this interface, I have to add a term in the Hamiltonian, which describes disappearance of 2 electrons from the semiconductor. So that's effectively a term which allows to break particle number conservation. Okay, so that's the proposal. So suppose we first take this one-dimensional system which has the Rajba spin-orbit coupling, and we also have some magnetic field along the longitudinal direction. And so what happens in this geometry that first this Rajba coupling separates the spectrum into 2 parabolas, but then this additional term essentially opens up a gap in the spectrum at 0 momentum. So at the end of the day, if the chemical potential is somewhere here, you will have a single Fermi surface. So it's going to be, if you have a single Fermi surface, which is kind of tricky because I started from a spinful system, but in the basis that diagonalizes this Hamiltonian, I will have spinless particles. I have single species of particles that live on this single Fermi surface. And so that's how we get around the fermion doubling due to the spin degeneracy. The nanowires actually that are useful for our purposes are indium arsenide and indium antimony nanowires, and for technical reasons they are very favorable. They have very large couplings to magnetic field, to Rajba spin orbit coupling, and they have very good contacts with metals. So now this is rather technical slide, but what I want to present the schematics, why this state, this complicated Hamiltonian, is related to this spinless p-wave superconductor. So you have, let's imagine that we have a wire that is lying on top of the superconductor, and then you'll have these additional terms due to the proximity effect. Then let's do the following trick. Let's first diagonalize this part, and then rewrite the other part in the basis that is diagonal, where the single particle part is diagonal. So what happens when the chemical potential is here, that essentially this band is unoccupied, and I can project the system. I can just keep the lowest band. And if I do that, all these terms that are here, I will throw away psi plus component. And so they are gone. And now what I'm left with is essentially a single component for single species. Now index minus is kind of a spin index. And I have a p-wave superconductor. Okay? So this construction allows us to map this spinful model to a spinless p-wave superconductor. And I showed you that spinless p-wave superconductors have 0 modes at the ends. So therefore, this model should have 0 modes at the ends as well. And you can see that these zero modes can be only if the chemical potential is somewhere in the gap. If the chemical potential is somewhere here, then this construction that I showed you doesn't work. So what we find that this system can generate Majorana fermions on demand. Okay, so I change some parameter in the system, and I can go from a state which has these modes to a state which doesn't have these modes. Okay, and you can keep all the details, keep the full Hamiltonian, and check these ideas numerically. So that's what you find. So this is the plot of the density of states as a function of the length of this wire. So this is the length, and the function of energy. And it's just numerical diagonalization of the Hamiltonian and then computing the density of states. And you can see that you have 0 energy states at the ends where the magnetic field is in the right regime. And in the opposite regime, you just don't have anything. So they disappear.
Just a technical question. What do you use to model Hamiltonian?
How we did that?
Graphs.
Oh, it's Mathematica plot. You can do many things with Mathematica these days.
Oh yeah, painfully, but yes.
Okay. All right, so that's basically the system that we would like to use to build our topological quantum computer. Well, one can also say, well, what if your theory is missing some important ingredients, and how do you test your theory? Well, there are simple experiments that one can do to test this theory. I mean, the fact that you have zero energy states in one phase and you don't have it in the other phase should be seen in the experiments. And the simplest experiment is to try some kind of a tunneling or scanning tunneling microscopy and try to tunnel at the end of this wire. If you have a state at zero energy, then the tunneling should be allowed. If you don't have it, then the tunneling should be forbidden. And what you should find, actually, there is a concrete prediction that if the state is in topological phase, then this tunneling conductance, the IDV, should be equal to something very universal, 2e²/h. And in the other limit, it should be exactly 0. So there are other experiments which also have very interesting signatures of these Majorana fermions in the system. But I just wanted to maybe talk more about quantum computation in this audience. I would be happy to explain more about experiments if somebody is interested in. So suppose we have this system, suppose we have this phase. What can we do with it? Well, by the way, this is how the current experimental situation, this is where the current experimental situation is. So actually we have these nanowires and we are doing the experiments as we speak. And, you know, we'll keep you posted once.
I think they're in bed in Copenhagen.
Okay. Yeah.
It's kind of late there.
Right.
How late those questions are.
Right.
Various objects on this picture.
So these are the gates that you can apply to change chemical potential in the system. And this is the wire lying on top. And beneath you have a superconductor.
Just a regular S wave.
Regular S-wave superconductor.
Like niobium metal at low temperature.
Yeah. So how can we use these systems for quantum computation? So the reason, there is a very interesting effect. So I mentioned that if I change the chemical potential somewhere, I can go through the phase transition, right? If I change the chemical potential, I can go from a state which doesn't support Majorana to a state that supports them, right? So suppose I change the chemical potential only in half of the system. Which means that if essentially I move this Majorana particle somewhere here. And essentially it allows me to move these particles and exchange them around. Because if I create now a T junction, so I can move this particle here, then move this other particle here, then move it back, and so on. I can do the exchange that, I can do the braiding operation that I mentioned before. So these wires essentially allow you to do braiding operations. The network of these wires allow you to exchange the particles. Because it's essentially a two-dimensional network of one-dimensional wires. And one can also measure the state of the system by coupling these wires. So this is the wire, and this is a set of gates, by coupling the system to a squid. So this is the squid, and you have 3 Josephson junctions. And it turns out that because the state is either occupied by an electron or unoccupied, these Josephson junctions, these squids, are sensitive to and they can distinguish different states with different fermion number. So I just measure some characteristic of the squid, like a splitting energy, and I will be able to distinguish the difference between the state occupied and unoccupied. So I can do the readout of the state.
So what are those tunnel barriers? Are they just fictional surfaces, or you can buy them at Home Depot or something like that?
No, you can get them for free actually. Right. So if you have an aluminum and expose the aluminum to the air, it will create a natural layer of oxide. And so this oxide is a barrier. And so if you basically take them out from the vacuum and then stick them together after that, and you'll have a junction.
They usually don't put them in the air. They're usually inside some chamber. But basically.
The basic idea is that they use oxides.
That's right,
Yes.
aluminum oxide. They could have done it in there.
So another thing that you can do, you can actually create a device which is called topological quantum bus. So, so I mentioned that the information that is encoded in these topological degrees of freedom is very different than the information that is encoded in conventional qubits, where the degrees of freedom are microscopic. So if you want to couple, say, conventional quantum architecture and topological quantum computation, we need to find a bus which can do that. And these are the ideas which allow you to do that. Again, it really helps that these are superconducting systems. And here's, for example, a proposal to couple a semiconductor double dot qubit where essentially the state is encoded by the presence of electron or absence on this dot. So, so that's one proposal. Another proposal is to couple this wire network with so-called transmon qubit, which is just the generalization of a charged qubit in superconductors. But what is interesting that one can then couple these superconductors to photons. And photons one can teleport, they can live over large distances. So here's the example. You have a strip line resonator, which it's basically a cavity with very good mirrors. And you can control the number of photons in this cavity by lowering the temperature. And essentially this photon couples to this transmon qubit, which is basically the qubit which consists of these two superconducting kind of islands, large islands. And then the transmon qubit couples to topological qubit. So bottom line, we also can use advantage of these conventional qubits to do the logical operations, which are very fast in those qubits, and then teleport information into topological space and store the information there. So I'll leave you with this final slide where we envision some kind of topological quantum computer. It's basically a computer which is in the delusion-free, but it's also connected to some classical machine, and you can just dial particular tasks that you want the quantum computer to do, and it will do the task and then spit out the result and communicate it to a classical computer. So with this, I will end, and thank you very much for your attention. Yes?
So you mentioned speed. Is that, so the topological computer tends to be slower than the other ways of doing quantum?
Well, you have to exchange the particles, which tends to be slower. Also,
are there other disadvantages that you're aware of?
Also, there is one gate that we need to teleport from somewhere from conventional computers. We know how to make many gates with topological, but there is one gate that is missing, and we would like to teleport this gate from the conventional quantum computers.
Yes, conventional quantum computers as opposed to...
Yeah. So it's I understand that quantum computing is already unconventional, but for the people in the field, it's kind of conventional, and then topological is unconventional.
But sort of as a follow-up, is there a limit, the one-dimensionality of it, does that limit what you can do with it? Or can you make a grid of those wires?
You can make a grid. There is no problem.
Yeah.
You can make actually various networks and study the properties of these
There's
networks.
no problem with them overlaying each other. You can
No.
the interaction between them.
Yeah, the key is edges and surfaces and so on. And if you can manufacture those in quantity, then you've got a lot of opportunity. That's all.
There was another question?
So how long before you expect to get results on
Well, it's not the right question to me.
Well, there's an amplitude, right?
Yeah. We hope soon. I mean, they started fairly recently. They actually started maybe in the spring of this year. So
6 weeks ago.
it's hard to predict, but they already have some good results. I mean, they've tested the parameters that we used, for example, for some estimates of these nanowires, and they find that they're in the same ballpark. So now they have to couple them to superconductors, and characterize that part. So
And they have to adjust the
chemical potential, tune into the right
Get
regime.
it to
Is this one of the experiments that you spend 2 years analyzing the data afterwards, or?
No, they will. This is not a high energy experiment. There, you just measure something that comes out and analyze it next day.
It'd be nice to measure 3 or 4 or 5 or 6 times to be sure.
Okay.
You'll know quickly.
What is the device you are using to try and observe the emergence of the Majorana Fermion?
So tunneling experiment, for example. So you just have some normal metal tip, which is in tunnel contact with the end of the wire, and you will tunnel and see whether this electron actually has some density of states to go into or not.
It's hard to see an individual electron, right?
No, but it's very easy to see dI/dV because you're just measuring electric signal. And this electric signal will be either 0 or something finite. In fact, not just finite, but something that is 2e squared over h, 2 times fundamental constants. So there is a very concrete prediction. This is though 0 temperature result. So if you have low temperature, sufficiently low temperature, which is doable.
Since this device has such high implication on cryptology, could it be, let's say, the NSA already have that and they just won't tell anyone?
Well, if NSA has it, then I don't know it. Okay, but there are some companies that are very interested in these devices, like Lockheed Martin, for example. So maybe they might have it. I don't know. Yes.
So I know there's some double beta decays experiments that are looking for Majorana.
Yes, in high energy physics, people are looking for Majorana fermions in double beta decay experiments.
So if they find that confirms that Majoranas can exist, but it doesn't necessarily mean this.
Exactly. Okay. So here in condensed matter, what we are predicting is actually more than just Majorana. We are predicting a state which has non-Abelian statistics and has degeneracy. It just happens to be that these particles at 0 energy, they satisfy Majorana condition. So once you find the Majorana in solid state, then it automatically should have these properties. But in high energy, it doesn't have to be the case.
Majoranas don't have a lot of measurement nicety for the high energy crowd, any more than neutrinos do, as a matter of fact. I mean, they just don't have a lot of properties that you can measure in a collider, for example.
But this double beta decay, I think that's the experiment that they try to do. And as far as I know, the data is inconclusive because there is not enough statistics.
Mm-hmm.
And they're trying to...
Enough events. I mean, it doesn't happen that often.
Right. They're trying to reproduce this experiment, but that costs a lot of money. It costs millions of dollars, if not more. I mean.
Here it's kind of interesting because the Majorana is trapped in the end of that wire. I mean, we know where it is if it is.
Right.
And so the tunneling knows where to look, I guess is the way to say it, right? You get to decide whether there's a Majorana there or it's just the end of these pairs,
Yeah. Exactly.
So what does that mean physically when you said that you change the chemical energy to kind of change the end point of the wire? Is that...
Yeah.
Chemical potential. I don't know why it's called chemical potential, but yeah, it's a...
What are you doing to the wire?
So see, I can have some gate on top, and I can change the chemical potential in the...
Are you adding electrical energy? What are you doing? What is it?
It's a capacitive coupling.
Okay.
Yeah, and what you're doing is you're changing the level where the states are occupied.
Exactly.
Right? So below it they're occupied, above it they're not. And you're trying to get...
Trying to tune that level.
You're trying to get this
Right.
thing at 0 energy by jacking that thing up so that it's a permitted thing. And it gets protected once you're there because of this
But this is
E minus E
electrical-
conjugacy.
This is an electrical change.
Yes.
In
Yeah.
the material, not like a physical...
Yeah, but we were talking yesterday about population changes. And I asked Roman, I said, so what are all the ways we can change the chemical potential?
Well, let's don't go there.
No, but I mean, but yeah.
There's lots of ways.
Yeah.
Yes.
There aren't that many people out there who can hack that kind of quantum mechanics. I suspect the NSA could not really do such a thing on the quiet. Now, the Russians and Chinese might be able to do it, but the NSA if 100 hot quantum people go to Maryland, right, that will be noticed.
Yeah. They actually created the institute, Joint Quantum Institute, so they already have a lot of people there.
Okay.
And some of the people in Maryland know where Fermi is too, so.
Okay.
Well, let's thank Roman again, and he'll